Welcome back. We were discussing the uncontrolled rectifiers. We completed our discussion on single phase and three phase uncontrolled rectifiers. In this lecture, we are going to summarize each and every components that we have discussed in terms of its performance parameters. So we will first introduce the different types of rectifiers, whether it is single phase or three phase, and compare their performance parameters. We will do the entire comprehensive comparison of each parameters, do the harmonic analysis, and see the design considerations that are required for industry grade rectifiers, the filter circuits required, and some of the advanced topics. Rectifiers, as we have discussed, basically convert the alternating current to direct current, and there are two main categories. One is the uncontrolled rectifier and another one is the controlled rectifier. Our focus is on uncontrolled rectifier, which is using the diodes. Controlled rectifier we will take up in the next lecture, where we will see the thyristors and use of silicon controlled rectifiers, how it is controlled the current and the voltage. Classification by phases, if we go, then it is single phase and three phase. So when we have single phase, it is basically talking about the residential low power application, and for three phase, it is generally industrial and high power application. Uncontrolled rectifiers are simple but have fixed output, and they are wide applications in power supplies, battery chargers, and DC drives. So single phase rectifier configuration may be half wave or full wave in the two configuration, either in the center tap form or in the bridge rectifier. So half wave rectifier will use one diode and it will conduct for half cycle only. It has poor efficiency and high ripple. Whereas full wave rectifier, when it is center tapped, it uses two diodes with center tap transformer. It conducts for full cycle and it has better efficiency than half wave. Full wave rectifier use four diodes, which is just the double of the center tap rectifier. It has better transformer utilization and it is most commonly used configuration in industries. Three-phase rectifier configuration, when we talk about, then it can be again in the form of half wave and full wave. So when it is half wave, we are using three diodes and it is connected to three-phase supply. Each diode will be conducting for 120 degree. It is simple but poor transformer utilization. When we have full wave configuration in the form of bridge rectifier, then we are using 6 diodes connected in the form of bridge. Each diode will conduct for 120 degree. Highest power applications we have, and it is best performance parameters. Three-phase full wave rectifier can also be connected in the form of center tap. It is also using 6 diode, but we have the center tap transformer connection. They have good performance but require special transformer arrangement. Some of the key performance parameters that are used to judge the quality of the rectification are the rectification ratio, which is the DC power efficiency. Form factor determine the shape of the output waveform. Ripple factor determine how much AC content you have on the output DC side. Transformer utilization factor determine the transformer efficiency. Peak inverse voltage determine the diode voltage stress under the reverse bias condition. Displacement factor is the phase relationship. Total harmonic distortion, we calculate the harmonic content in the waveform. Power factor is what we determine the overall power efficiency. Conduction efficiency determine the voltage regulation. Voltage regulation we determine for the load stability. And Crest factor is basically the peak to RMS ratio. So these are the performance parameters that need to be compared among different configuration of the rectifiers. So rectification ratio is basically the ratio of DC output power to AC input power. So it is the ratio that we compute in terms of power. And when it is DC power, it is basically the product of voltage into current in the DC. And when it is AC, we are taking the RMS to calculate the voltage and the current. The rectification ratio of the different rectifiers from single phase to three phase configuration, if we see, then half wave rectifier is having 0.2 as the rectification ratio for single phase half wave. Full wave center tap is 0.405. The single phase bridge rectifier is 0.8, and three phase configurations are correspondingly from 0.2 and 1.3 respectively in the center tab and bridge configuration. So it is to be noted that higher rectification ratio indicate better power conversion efficiency. So we should have the higher rectification ratio possible. Form factor, which is the ratio of the RMS value to the average value of the output voltage or the current. So we need to determine the form factor either in the form of voltage or in the form of current, and it is the output by the input. So output is basically we take as the RMS voltage, and the input we take as the DC whatever we have. So it is the ratio of RMS by DC, and it is the rectifier. So we are converting the AC to DC, and this form factor is determined for the different configuration similarly to the rectification ratio. So we can see the different configuration from single phase to three phase, its corresponding form factor. So form factor is quite good when we talk about the different configuration. As single phase half wave, it is 1.57. So lower form factor indicate output closer to pure DC. So basically output we require as pure DC. So form factor should be as low as possible. So we should have the lower form factor. Ripple factor is a measure of the output where we have the AC component present relative to the DC. So output should be DC, but there are certain AC component present that are known as ripples. So this ripple factor is determined using the formula of form factor. So under root of form factor square minus 1, which is again the ratio of AC to DC voltage. So ripple factor of different configuration, if you see it, then the highest ripple factor we get it for single phase half wave, which is 1.21, and the least ripple factor we get in the form of three phase bridge configuration. So corresponding ripple frequency, if we see, then highest ripple frequency is 6 times the fundamental frequency for three phase, and the lowest ripple frequency is for single phase half wave. So the goal that we have is lower ripple factor, which indicate better DC output quality. Three phase rectifiers have much lower ripples. So the lower ripple factor indicates that yes, the output is having the better DC quality. Conduction efficiency, which is again the ratio of DC output power to AC input power, and it is related to the form factor. So efficiency is basically the ratio of DC to AC, and we can relate it with form factor, which is form factor square into 100. So if we determine the conduction efficiency, the highest conduction efficiency we can see 97.3% for three phase bridge rectifier, and the lowest one is 40.6 for single phase half wave. The other one in single phase we have 81% for full wave and 96.8% for three phase half wave. So the observation is three phase rectifier have significantly higher conduction efficiency. So we need to go with three phase when we need more efficiency, especially in industrial applications. Transformer utilization factor, which is the ratio of DC power delivered to the load to AC rating of the transformer second wave. So we have a transformer with input and output. So we are dealing with the secondary of the transformer. So transformer utilization factor is basically the ratio where the numerator we have the DC power and the denominator we are having the AC power. So product of RMS voltage into RMS current on the secondary side of the transformer. Transformer utilization factor, if you see, then the best transformer utilization factor we get for three phase bridge rectifier, and the poorest one we have for single phase half wave rectifier. So significance what we have is three phase bridge rectifier has the highest transformer utilization factor, indicating the best transformer utilization. The peak inverse voltage, which is the maximum reverse voltage a diode must withstand when it is reverse biased. So when the diode is reverse biased, how much voltage it has to withstand? So that we need to determine. So if we compare the peak inverse voltage of the different configuration, we see that root 3 times Vm is the one which is taken by the three phase configurations, whether it is in the form of half wave or bridge configurations, and other diodes configuration, whether it is half wave, we have Vm as the maximum voltage as the peak inverse voltage. 2 Vm we have for single phase full wave and Vm for single phase bridge rectifier. So we need to do proper design consideration where the peak inverse voltage rating determine the diode selection. So it is the three-phase system where the peak inverse voltage is the highest, which is √3 times the line voltage peak. So when we take the safety factor, then the practical diode rating is equal to the peak inverse voltage, whatever we got it here, multiplied with certain safety factor. Typically, this is taken as 2 to 3 times. So again, the maximum reverse voltage that the diode need to withstand should be having the safety factor also into account. The Crest factor is the ratio of the peak value to RMS value of the input current. So Crest factor we are determining as the ratio of peak value of the current to the RMS value of the current. And the different configurations Crest factor if we determine, so all comes to be practically equal to 1.414, which is √2 times. So high Crest factor indicate high peak current requiring robust components and causing stress on supply system. So it will cause the stress on the supply system. So high Crest factor is not good because it will be indicating high peak current. Total harmonic distortion, which is the measure of harmonic content in the input current relative to the fundamental. So fundamental frequency is the one which we are more interested in. And other component of frequency, which is in the form of integer multiple of n, those are harmonics. So we are calculating the total harmonic distortion, taking the integer from 2 to infinity in the current waveform in square, and 1 indicate the fundamental component of the RMS current multiplied with 100. So if you see the total harmonic distortion, the maximum one is in single phase half wave and the minimum one is in the three-phase configuration. So IEEE standard limit the total harmonic distortion should be less than 5% for the system having the voltage greater than 1 kilovolt and less than 8% for system having less than 1 kilovolt. So we need to obey the IEEE standard when we are designing the rectifiers in terms of total harmonic distortion. Power factor is the ratio of the real power to the apparent power and considering both the distortion as well as the displacement. So power factor is the product of displacement factor into Crest factor, and it is the ratio of the real power by apparent power, which is I1 by IRMS. Power factor, again, if we compare, then we see that the highest power factor, we get it again in the three-phase bridge configuration, and the poor power factor is in the single-phase half-wave. So the practical impact that we have is low power factor will result in higher utility charges and reduce system efficiency. So as the power factor is low, we need to pay more electricity bill because the reactive power will be more and the real power will be less. So we have already discussed in very detail about the power factor correction techniques in the previous lectures. Voltage regulation is a measure of how well the output voltage remains constant with the load changes. So when the load changes from no load condition to the full load condition, then what is the change in this voltage? The reference we are taking as full load into 100 is the voltage regulation. So the factors which affect the voltage regulation may be the source resistance and the reactance. The diode forward voltage drop, typically it is 0.7 volt for silicon, transformer resistance and the leakage reactance, and the load current magnitude. So these are the factors which affect the voltage regulation. In the three-phase system, generally we'll have the better voltage regulation because of lower ripple content, more continuous conduction, and better transformer utilization. So again, the three-phase system will have the better voltage regulation as compared to the single phase. So the goal is to have the lower voltage regulation percentage, which will indicate the better load stability. So we have to deal with the stability of the load. So voltage regulation should be as low as possible. Now this is a complete comparison of the single phase rectifiers in the form of half wave, full wave or bridge configuration in terms of different performance parameters. What we have discussed, the rectification ratio, form factor, ripple factor, conduction efficiency, transformer utilization factor, peak inverse voltage, total harmonic distortion, power factor, Crest factor, number of diodes, and the ripple frequency. So when we compare these configurations, generally the full wave will be better than the half wave in most of the cases. But the full wave obviously will require more number of diodes. The same type of comparison we can do for the three phase, the same performance parameters, And here we have two configurations, either in the form of half wave or in the form of full wave, which is the bridge. And we can do the comparison here. So we can find that the three-phase bridge configuration, which is the full wave, is better as compared to the half wave. And again, the number of diodes will be more as compared to the half wave. So cost will be more. When we do the harmonic analysis for single phase configuration in the form of half wave or full wave, we can do the voltage, which is break up into different fundamental frequency and the different harmonic frequency. So here you have omega t, 2 omega t, and so on. So this is for half wave and the full wave. So if we do the half wave, the dominant frequency is dominant harmonics having component DC, which is Vm by pi, and fundamental is about 50%. Second harmonics, fourth harmonics will keep on reducing, which is the dominant one. In full wave, the DC is 2 Vm by pi, which is double of this half wave. There is no fundamental here in full wave, and the harmonics that we have dominant is second, fourth, and sixth in the percentage as 42.4%, 8.5%, and 3.6%. Three-phase harmonic analysis, if we do, then this is the voltage equation for three-phase bridge output. Voltage harmonics and current harmonics, both we can find out. The voltage harmonics, we have the DC, which is 3 root 3 Vm by pi, which is approximately equal to 1.654 Vm. And the dominant harmonics in voltage are 6th, 12th, 18th. And generally, it will be having only 6 nth harmonic present. So it is multiple of 6. Current harmonics, you have 5, 7, 11, and 13. So it will be characteristic as 6n plus minus 1 time in the current harmonics. So what are the advantage? Three-phase rectifiers have much lower harmonic content, especially at lower frequencies. So when we do the harmonic analysis, we find the three-phase configuration is better as compared to single phase, especially at the lower frequency. Now, in terms of applications for single phase and three phase, we can do the comparison that if the power is less than 5 kilowatt, go with single phase. Power greater than 5 kilowatt, you go with three phase. Residential application usually will have single phase. Industrial application, three phase. Small motor drive, single phase. Large motor drive, we go with three phase. Better battery chargers usually take single phase application. DC transmission system take three phase. Electronic equipment will have single phase application. High power supplies will have three phase application. So three phase supply where it is unavailable, we are going with single phase applications, and where we required low ripple, then we required three phase application. Single phase have certain advantage like it is simple control, lower cost, and ready available supply. Three phase will have higher efficiency, lower ripple, better volt power factor, and smaller filter requirement. So each single phase and three phase have their own advantage and disadvantage, and they are apply for different applications depending upon the power requirement. We need to do the component selection guidelines following from the diode selection, transformer rating, and the filter design. So we need to do the current analysis, whether it is average current or peak current. The reverse voltage also we need to determine the recovery time of the diodes. Transformer, we need to compute as the VA rating based on the transformer utilization factor and the safety margin. Voltage regulation under full load condition. What is the temperature rise and insulation class? Short circuit withstand capability we need to do for the transformer. We need to calculate the value of the capacitor that is required for the filter proper design. The inductor will reduce the current ripple, which will be improving the power factor. The LC combination will have the best performance, but will have the higher cost. So whenever we design a rectifier, we need to have the proper selection of the diodes, transformer, as well as the filter design. Filter circuit requirement for a single phase and three phase, if we compare, then ripple content is higher, which is 48.4% in single phase, but it is much lower ripple in three phase, around 4.2%. Larger filter will be required in single phase as the ripple content is quite high, and smaller filter requirement will be there in three phase for the same reason that the ripples is quite less. Second harmonic is dominant in case of the frequencies around 100 to 120 Hz. Sixth harmonic is dominant in the range of 300 to 360 Hz. Capacitor filter are the most common for single phase, and in three phase often no filter needed for certain applications. So the formula of determining the capacitor value or the inductor value to design the LC network filter design depend upon the current which is flowing in the load, what is the voltage ripple and the current ripple, and we can use this formula. So advantages what we have is 10 to 30 times the smaller capacitors we can go with this. It has lower cost and size, better dynamic response, and less energy storage. So LC network has this advantage. Economic impact, if we go, then three-phase system require significantly smaller and cheaper filter components. So if the ripples are present in the supply, then we need to go with the three-phase system compared to the single phase. Commutation and overlapping also need to be properly judged. So commutation process, which is transfer of current from one diode to another, is generally affected by the source inductance, and we create the commutation notches in voltage. Overlap angle mu, which is the period during which the two diodes conduct simultaneously, this reduces the output voltage. So the formula that we use for the overlap angle to determine the DC voltage is VDC equal to VDC naught cos of mu by 2. So this is more significant in three-phase system. So there are certain effect of source inductance. It will increase the overlap angle, reduce average output voltage, improve the current continuity, and it will create the voltage notches. So practical consideration we need to do as the source inductance is unavoidable and must be considered in real design. So inductance plays a very important role. This is the source inductance. We need to do the proper design. Otherwise, we will be having the voltage in the notches and there will be reduction in the output voltage, and it will having problem in the commutation as well. So the key takeaways from our discussion is single phase rectifier when we discuss, then it is the bridge rectifier which is the best choice. Efficiency up to 81.2%, but high ripple we have 48.4%. It is suitable for low power application less than 5 kilowatt. Three phase rectifiers are superior performance in all parameters. Bridge offers 97.3% efficiency with the least ripple 4.2%, and it is essential for high power industrial application. So selection criteria will depend upon the power level, supply availability, whether it is single phase or three phase, ripple requirement and filter cost, power factor and harmonic regulation, initial cost versus operating efficiency. So this selection criteria will judge whether we need to go with the single phase or three phase configuration. So again, we can compare the single phase and three phase in a better way with these performance parameters, and depending upon our requirement, we can go with either the three phase or single phase with the proper judgment of the performance parameters that we required. So recommendation that we have is for most applications, single phase bridge will have the power less than 5 kilowatt and three phase will have a greater than 5 kilowatt. So if our load requirement is more than 5 kilowatt, we need to go with the three phase bridge configuration. Some of the contemporary applications of these rectifiers is in the form of renewable energy, industrial applications, electric vehicles, and power quality. So renewable energy nowadays is growing a lot, and more advantage we are getting as the energy demand is increasing. So inverters will be there, where the solar PV system, which is the conversion of DC to AC, wind turbine rectifiers will be there, battery charging system and grid tie applications will be there. Industrial application, whether we talk about the drives, motor drives, electroplating or welding, there also rectifiers are required. Electric vehicles, onboard chargers, fast charging system, motor drive system and braking in the form of regenerative, we required the rectifiers. Power quality in terms of active power filters, harmonic mitigation, power factor correction and grid support system, also we required the rectifiers. Some of the future trends and challenges for the researchers, as we have discussed in the previous lecture also, that wide bandgap semiconductors now plays a very important role in the form of silicon carbide and gallium nitride diode, which is replacing the silicon. It has the higher efficiency and switching speed, better temperature performance and reduced size and weight. So a lot of researchers are going on in these semiconductors. Smart grid integration we need to do with bidirectional power flow, grid stability and support functions, real-time monitoring and control, and distributed energy resources. Regulatory challenges are there in terms of IEEE 519 standard, which is the harmonic standard, energy efficiency regulation, some form of interference, which is EMI and EMC interferences, compliance requirement is there. Grid codes will be required for renewable integration. Let us do some design example with the single phase bridge rectifier. So if you have 230 volt 50 hertz supply with a load of 2 kilowatt resistive load, we need to determine all the performance parameters. So whatever the formula we have seen, we need to determine that in terms of this voltage and the load requirement. So when you have the 230 volt, we need to convert that to the maximum voltage, which is 230 into root 2. DC voltage will be, because here we have the single phase bridge, so it is 2 Vm by pi. So we need to calculate. IDC is nothing but power by voltage. Power is 2 kilowatt and voltage what we have compute here. So it is 9.66 ampere. IRMS is IDC into form factor. So IDC is 9.66 multiplied with form factor, which is 1.11 in case of sine wave, which is 10.72 ampere. Ripple factor, we know for single phase bridge, it is 0.482 from table. Peak inverse voltage is nothing but the maximum voltage that the diode has to withstand in the reverse biased. So that is 325.3 volt. Efficiency will be 81.2% from table. Transformer utilization factor will be 0.812. Again, if the configuration is three phase in the bridge rectifier format, if the line to line voltage is 400 volt with a 50 hertz supply, 10 kilowatt load, we need to do the calculation of all the key parameters and compare it with the single phase. So now the line voltage will be 400 root 2 because 400 is the line to line voltage. DC voltage is 3 root 3 multiplied with Vm by pi, which is 540.5. IDC is power by voltage, which is 18.5. IRMS, IDC into the form factor again 1.014. Ripple factor is 0.042, which is 11.5 times better than the single phase. Peak inverse voltage is root 3 times the Vm, which is greater 565.7. Efficiency is 97.3%, quite good as compared to single phase, which is 81.2. Filter size approximately 1/10 of single phase requirement. So some of the laboratory experiments suggested, one is to do with the single phase rectifier to build the half wave, center tap and bridge rectifiers, measure all performance parameters, compare the theoretical versus experimental result and observe the waveform with oscilloscope. We can do the MATLAB simulations also for single phase and three phase. So this construct the three phase bridge rectifier, measure the ripple factor and efficiency, compare with single phase bridge. Harmonic analysis you do with the spectrum analyzer for three phase rectifier analysis. And filter circuit investigation we need to do, determine the different types of filter design in the form of inductor, capacitor, combination of LC and RC, do the ripple reduction versus filter component values, voltage regulation with different loads and current waveform distortion analysis. So these are some of the suggested laboratory experiments that we can do to have a quick, good understanding of the rectifiers. So this complete our discussion. This was just the revision of all the rectifiers performance parameters. We have discussed in very detail about each rectifiers in the previous lectures. In the coming lecture, we will now discuss on the controlled rectifiers. Uncontrolled we have completed. So we'll go with the controlled rectifier where we will introduce the thyristors. Thank you for now.